So in this video, we are going to prove the circle theorem that the angle at the center of a circle, so this guy here, is twice the angle at the circumference standing on the same arc. So we are talking about the arc over here, okay? So we can see this arc subtends both of these. Now, in order to prove this, we're going to do this proof for two different cases. The easier one is this first one. Now, what we're going to do with this particular proof is we are going to, like we've been doing so far, try to break this up and separate this to create some triangles. So I'm going to draw this dotted line in here, okay? So with this in mind, I'm going to let angle ABO be, let's call it alpha, and I'm going to let angle CBO be beta. Okay, so let's just label these in. So this guy's going to be alpha. And this one here is going to be beta. Now, let's think back to what we know about isosceles triangles, because by doing this, we can see that we've formed two isosceles triangles because we have equal radii. So in triangle BOA, BO and AO are the same. So we're going to say in triangle BOA, AO equals to BO because these are equal radii. Okay, now with this in mind, we can say that angle OBA or ABO equals to angle BAO. So we can say angle ABO equals angle ABO equals to angle BAO. And the reason is that these are angles opposite equal sides in a triangle. So we can say angles opposite equal sides in a triangle are equal. Okay, so with that in mind, we can say that this one is A as well. Now, similarly, we can say that angle BCO, equals to angle CBO. So, because we have another isosceles triangle here, we can say that this is angle B. Now, I've given these different names because we can't assume that these angles are the same. So I'm going to call one alpha, which is one size, and one beta, which is another size. Now, in order to do the next bit, we need to remember a particular relationship with the angles in a triangle. Now, thinking back, when we draw up a triangle, there's a relationship between the exterior angle and the two opposite, let's actually get it off this, one moment, between the exterior angle and these two angles on the inside. These two are actually equal. So if we remember, the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So with that in mind, we can say that this angle out here, let's give this another name, let's call this D. We can say that angle DOA equals 2 alpha. Now, the reason is the exterior angle for a triangle is equal to the sum of the two interior opposite angles. Good, okay, so with that in mind, we can now call this angle 2 alpha. Also, we can say the same thing for this angle DOC. We can say, similarly, angle DOC equals to 2 beta. So we can label this guy 2 beta. Now, here is what this basically brings us to the proof that we are trying to do. Now, we're trying to prove that this angle AOC is double this angle ABC. So we can say that angle ABC, its size is alpha plus beta. Now, angle AOC equals 2 alpha plus 2 beta. As we see down the bottom, it's the sum of these two angles. So, doing a little bit of algebra, we can factor out this 2 as a common factor. And we can see that AOC is 2 lots of alpha plus beta, which is the angle ABC. So this equals 2 lots of our angle ABC. So we have therefore proven that the exterior angle here, AOC, this guy, is twice the interior angle. Now, looking at a different way this proof can look is with this example here. Now, in our previous one, we could see that it all looked quite nice because we could just draw this line straight through and it looked really simple, and we just made our two isosceles triangles and that was it. This time, we don't really have that same luxury, right? We're trying to prove that this angle here, I'll make the writing a little bit smaller, that this angle here is half of this angle at the center. Because remember, these are still sharing the same arc BC, but we're trying to prove that this one is twice, the one at the center is twice the angle at the circumference. Now, I won't be as formal with the proof, just so we can get through it a little bit quicker, but feel free to pause this video and try to do it on your own. What I'm going to do instead is I'm going to join up O and A like this. And what we've essentially done here is now we've actually made isosceles triangles. Might not be immediately obvious to see, but if you look at this one here, that's an isosceles triangle, OAB, because OA is equal to OB because of the equal radii. And we have this triangle OAC in which it's isosceles because OA equals OC because these are equal radii. So I'm still doing essentially what I did last time, but I'm doing it in a slightly different way. Now I'm going to let angle OAC, this guy here, be alpha. And because I know that that one's alpha and these are isosceles triangles, this guy is going to be alpha as well. Now, I'm going to give this angle in here, my other triangle OAB, I'm going to call this angle beta. Now, because this is isosceles, it's the same, this side is the same as this side, then this angle here, angle OAB, has to be beta as well. Now, not to be confused with this little one over here. The entire angle here has to be beta because it is an isosceles triangle. This entire one has to be the same as this one. But I want to work with this little angle in here. Now, if I know the big angle, the entire one is B, and this little one is A, I can call this angle in my triangle beta minus alpha. Now, what we're going to notice is something about this particular angle here. Do you notice that, once again, this is an exterior angle to this triangle in here? So thinking back to what we know that this angle on the outside, the exterior angle, is equal to the sum of the two interior angles. So I'm going to actually write that here. Exterior angle, and let's give this another point so we can give it a name. This is angle ODA. We can say that ODA equals to beta plus beta minus alpha. We know this because of that same theorem, that same reason that we gave in the previous example, where the exterior angle of a triangle is equal to the sum of the two interior opposite angles. Now, cleaning this up with a little bit of algebra, we can see that this gives us 2 beta minus alpha. Now, this guy is 2 beta minus alpha. If you notice though, this thing is also an exterior angle to this triangle in here. So we can say that the exterior angle, 2 beta minus alpha, is equal to the sum of these two interior opposite angles. Now remember, we're trying to find angle BOC. We're trying to find this angle here and show that it's two lots of this angle at the circumference, beta minus alpha. So we're going to say that we're going to let angle at the center let's call this COD. B, let's call this X. Now, we know that the exterior angle equals to the sum of the two interior opposite angles. So this guy's X here. Now, I can say then that 2 beta minus alpha equals to X plus alpha because of that same thing we were talking about before. Now, rearranging this, I want to get the X on its own. So I'm going to subtract alpha from both sides. So I get that 2 beta minus 2 alpha is equal to X. I can factor out the 2 again. And I have shown this same relationship. Remember, the angle at the center is meant to be two lots of the angle at the circumference sharing the same arc BC. So the angle at the circumference is beta minus alpha. And the angle at the center, as we have shown, is two lots of beta minus alpha. So we have now shown that even in this particular case, which is a little uglier, the angle at the center is still twice the angle at the circumference. That brings us to the end of the video. Thank you so much for watching, and I'll see you next time.